Hi folks, we're going to go through this investigation, operating with radicals. Radical is just another word for a root, and we saw that roots were in fact equivalent to a fractional exponent. So we're going to see if we can use that property to see if we can find ways to operate with roots directly. Okay, so first thing to do is um, prove these two um, properties, and that's what's going to allow us to determine ways to operate with these radicals. Okay, so here in order to prove this equality, you start with one side of the equation and you manipulate it algebraically until you get to the other side of the equation. So I'm going to start with the left here, and I'm going to rewrite, so the left-hand side. Okay, and again, we know that the nth root is equivalent to the exponent 1 over n. Okay, so I'm going to rewrite this as ab to the 1 over n. But now that I have it written in exponent form, I can make use of my exponent rules. Okay, and here we can distribute that exponent to each factor in the bracket. So this can be written as a to the 1 over n times b to the 1 over n. And then each of these, because it's exponent 1 over n, can be written as nth roots. So this is just square root of, nth root of a times the nth root of b, and this is equal to my right-hand side. Okay, so what this tells us here is if I've got two roots, similar roots, okay, I can bring them together by just multiplying each input into those roots. Okay, not surprisingly, there's a similar rule for division. Okay, and again, we'll just show that here. So I'm going to rewrite the left-hand side as a over b to the 1 over n. Again, I can distribute the exponent to numerator and denominator, so a to the 1 over n over b to the 1 over n, which of course is now just the nth root of a over the nth root of b, which is just equal to my right-hand side. Okay, so we're going to see how we can use these properties to help us come up with ways for simplifying and operating with radicals. Okay, so let's go to number 2. So here, if we want to simplify these two, now we know that it's all about multiplying the individual numbers and bring them under the same root. So this is here the square root of 6 times 24. Okay, so here, let's see, 6 times 20 is 6 times 20 is 120, and then 6 times 4, 24, so 120 plus 24, 144. Okay, don't always need a calculator there. So this is the square root of 144, and now I recognize that as being a perfect square. Okay, so we started off with two non-perfect roots, and by doing our algebra, we saw that it was indeed equal to an integer. Okay, we can do the same thing, something similar with cube roots here. So here we've got the cube root of 18 times 12. So let's see if we can do this in our head. So 18 times 10 is 180. And then 18 times 2 is 36. So 180 plus 2 plus 36, 216. Okay. And now let's see, cube root of 216. Is that a perfect cube? Well, let's see. We've got 5 times 5 times 5 is 125. And 6 times 6, so 36 times 6 is indeed 216. So there we go. We have the cube root of 216. Again, what started off as two non-perfect cubes turned out to be a perfect cube that we could evaluate. Okay, and here again something similar. We have the same root, so we can bring them under the same root sign. 8 times 4 is 32, and the fifth root of 32 is just equal to 2. Okay, so we already see one way to use this property is to bring this product under one root, and we can simplify it. Okay, now in each of these cases, though, it just happened to be a perfect square, a perfect cube, perfect fifth root. Okay, but let's see how we can take this a little further. So it asks you here to consider how you could use the above property, so either one of these, okay, as well as perfect roots to write the following radicals in a simpler form. So it's this perfect root here that I want to focus in on. So I look at 72. Okay, and what I want you to think about is, are there any perfect squares that are factors of 72? Okay, so go through your factors of 72. So there's 8 times 9. Well, that's got a perfect root. So let's actually take that. Okay, let's see if there's any others. 2 times 36 is equal to 72. I'm actually going to do it both ways to see that we're going to end up with the same answer in the end. So if I start with rewriting 72 as 2 times 36, okay, now I can use the property that I found before. So this becomes square root of 2 times square root of 36. And then, lo and behold, square root of 36 is a perfect square. Okay? And normally we put the integer number first. So this can just be written as 6 root 2. Okay? So now, still have a root, but at least it's a simpler root to deal with. Let's see what would have happened if we didn't realize that 72 was 2 times 36. But if we had worked with root 8 times root 9, okay? Same thing would happen. You realize, well, root 9, that's just equal to 3. Then you might have noticed, wait a minute, 8, so here we'll put the 3, can be written as 4 times 2. Okay? And so this is just going to be the square root of 4 times the square root of 2. So the square root of 4 is 2. Square root of 2 can't simplify, and in the end, I still end up with 6 times square root of 2. Okay, so even if you don't find the largest perfect root right off the bat, if you just keep plugging away at it, you'll, in the end, get to the correct answer. Okay, so let's take a look here. Cube root of 48. Okay, so think of some perfect cubes that are factors of 48. And you go, well, 6 times 8 is 48. So this can be written as cube root of 8 times cube root of 6. And 8 is a perfect cube, just equal to 2. Okay, let's think of fourth roots here. Okay, so 80. And sort of think, well, 2 times 40. Okay, 4 times 20. Okay, let's see. Oh, how about 5 times 16? Okay, let's take a look. 5 times 16, so 16 times 5, that's 50 plus 30. Yeah, that's equal to 80. Okay, so this can be written as the fourth root of 16 times 5, which is the fourth root of 16 times the fourth root of 5. And fourth root of 16. 16 is a perfect fourth root, so that's just 2 fourth root of 5. Okay, so now we've used this property to help us simplify these larger roots into expressions that contain smaller roots. Okay, let's keep going. So here it says, while there are no rules for sums of powers, or I guess differences of powers, and you think of your exponent rules, and we do not have any rules for the sum of two powers or the difference of two powers, maybe we can still find a way to simplify these radicals here. So here, I've got square root of 3. I want you to think of 12. Well, 12 has a factor that's a perfect square, 4. So if we write this now, square root of 3 plus, I would expect that you should be able to skip this step, okay, after a while, but let's just write it out as 4 times 3. And you realize that that second radical can be written as 2 root 3. Okay, but let's take a look at what we have here. We have 1 root 3, and we're adding 2 root 3's. Well, how many root 3's do you have in all? You have 3 root 3's. Okay? Here you realize that you can add these expressions in a similar way that you can add expressions with variables. You have 1 of this object plus another 2 of this object, so you have 3 of this object in total. And so now we've managed to take this expression that has a sum of 2 radicals into one single radical expression. Okay? Let's see if we can do something with these here. Okay, if we can end up with the same cube root. So here, let's take a look, 56. Okay, well again, we think 56 now. Okay, so 56 is 8 times 7. Okay, so here we've got cube root of 56 is the same thing as cube root of 8 times 7 minus here the cube root. Well, are there any perfect cubes? Again, 8 times 2. So cube root of 8 times 2. So here we've got cube root of 8 is 2, so this is 2 root 7 minus, and this here would just be 2, sorry, not root, but 2 cube root of 7 times 2 cube root of 2. Okay, now you were able to simplify both of these, but you realize that there's no way to bring these together. So here, the only reason why we were able to bring these together was because we had the same square root. Here we do not have the same cube root. Okay, so don't be lulled into thinking that you can always bring them together. You could, however, write this as 2 times cube root of 7 minus cube root of 2. So you could do a little simplification here. Okay, let's see if there's anything to be done with this one here. Okay, so here 45 and 20. Well, this has 9 times 5. Okay, so and here, well, we've got 4 times 5. Okay, and this does look promising because this is the same as 3 root 5 plus, and this is the same as 2 root 5. And so now we can bring these together. So 3 plus 2, we end up with 5 root 5. Okay? So again, we notice how we do not have a general rule for adding and subtracting radicals, but when we've got this nice scenario that turns out to be the same radical, it can work out nicely. Okay, let's move on to number 5. Okay, now one of the things that's a general convention in mathematics, although you'll find that at times people aren't quite so picky about this, but certainly it is a convention in mathematics, is to not have a radical in the denominator. Okay, so if you solve a problem and you end up with an answer like 1 over root 5, okay, question is, how do you change this into an equivalent expression? So notice here you can change the form, but without changing the value. Okay, so here you have to ask, well, so first of all, you've got a fraction. I want you to keep in mind that if I multiply or divide a number to both the numerator and denominator, I don't change the value of the fraction. Okay, can't add or subtract, that will change the value, but if I multiply or divide the same number to numerator and denominator, I do not change the value. So this is where we're going to try to figure out how to solve this here. Okay, so here you got to think to yourself, is there something I could multiply to square root of 5, okay, that would, make it equal to an integer, okay, and not a root? You realize, well, wait a minute, if I multiply root 5 by itself, root 5 squared is just equal to 5. So the way in which we deal with this here is, if I need to multiply the denominator by root 5 in order to get an integer, as long as I do the same thing to the numerator, it's a perfectly legal operation. So here we have 1 times root 5, so root 5 in the numerator, and then here root 5 times root 5 is just equal to 5 in the denominator. And so these two expressions are exactly equal in value, but they now do not have a radical in the denominator. Okay? So here, you look at this one here and you say, well, you can multiply numerator and denominator by root 20, and that would work fine. But here I want you to keep in mind here, this root 20 can be simplified. Okay, so now whether you do it at the beginning or at the end, but often it's usually better to simplify at the beginning. So I have root 3 over, so this is 4 times 5, so square root of 4 is 2, so this is 2 root 5. So in the end, I don't have to multiply numerator and denominator by root 20, I can just multiply by root 5. So in the numerator, we've got, well, root 3 times root 5, which we know using our original property we can write as root 15. And here we've got 2 root 5 times root 5. So these two multiply to 5. 2 times 5 is 10. Okay? let's take a look at part C. Okay, here, though, you don't have a square root. If I multiply cube root of 6 by the cube root of 6, well, that's not going to give me 6. So what would I have to multiply here? Okay, well, in order to get 6, I'd have to multiply cube root of 6 times cube root of 6 third time cube root of 6. So I'm going to have to multiply by cube root of 6 squared. But of course, if I do that to the numerator, I'm going to also have to do that to the denominator. Okay. Now, just as an aside, one thing you think of in order to justify this, just in case you're not sure, cube root of 6 can be written as 6 to the 1/3. So think about it. If I need to get to 6, what do I need to multiply this by? Remember, we'd be adding exponents if you're multiplying powers with the same base, and you realize you'd have to multiply that by 6 to the 2/3, so that 1/3 plus 2/3 is equal to 1. And now that makes sense because 6 to the 2/3 is equivalent to that expression there. Okay? Oh, let's not forget the square. So here, this is 2 times cube root of 6 squared over 6. Now here we see that the 2 and 6 will simplify to 1/3. And now in terms of just writing this in a slightly nicer way, remember that when I have 6 to the 2/3, I could do cube root of 6 squared, or I could do 6 squared inside a cube root. So I'm going to switch these over, and I'll write that as the cube root of 36 divided by, and now I've simplified the fraction, divided by 3. Okay. Now you won't see this type of scenario with cube roots. I mean, usually, certainly the ones we're going to deal with in this course will all be square roots. Okay, but just to show you that this could be extended to other types of roots. Okay. Let's now get to D, E, and F. Okay. So we want to get rid of this root 2. But if I just multiply numerator and denominator by root 2, if I multiply denominator by root 2, I'm going to have to distribute it to both terms. So I'll get rid of this root, but I'll create a new one there. Okay, so not quite so easy to just get rid of it. So we're going to have to try to think of something. And I give you a little hint here. I ask you to consider a difference of squares. Okay, so if you think of a difference of squares, you've got, say, x plus a times x minus a. Okay, and what happens when you multiply these two expressions? Okay, FOIL, you got x times x squared, and the middle terms always cancel out because you got minus ax plus ax, okay, and then minus a squared. These always cancel each other out. Okay, notice here you have 1 plus root 2. What if I were to take this and multiply it by 1 minus root 2? Well, again, it's going to give us a difference of squares. The middle terms, negative root 2 plus root 2, are going to have to cancel out. But what are we left with? We're left with the squares of the first terms. 1 times 1 is just 1. And the square of the second terms. Okay, but the second term is a square root. So when I multiply it by itself, I'm no longer going to have a square root. I'm going to have whatever integer lies inside that root. So you see how we make use of this difference of squares idea, okay, that it gets rid of those terms in the middle, okay? And so that's the method for removing a root in the denominator, okay, when it's part of a larger expression. So, of course, though, if I do that to the denominator, I have to do the same thing to the numerator. So in the numerator, I've got 1 minus root 2. And the denominator, I've got 1 times 1. Okay. The middle terms always cancel out. Okay. So negative 2 plus root 2 cancel out. And I'm just left with root 2 times negative root 2, which is minus 2. Because root 2 squared is just 2. So in the end, what are we left with? Well, this is negative 1. So I'm left with negative 1 minus root 2. Okay. Similarly here, okay, I'm going to multiply, and this is what we call the conjugate. Okay, so if you have a binomial and you just keep the two terms and just change the sign in between, that's called the conjugate. So I'm going to multiply by the conjugate of 4 minus root 3, which is just 4 plus root 3. So again, same thing in the denominator. Okay, so in the numerator, I'm left with 4, so I'm left with 16 plus 4 root 3. And in the denominator, well, again, the middle terms cancel out. 4 root 3 minus 4 root 3. Okay, so I'm just left with the outside terms. So 4 times 4 is 16, minus root 3 times root 3 is just 3. Okay, so we're left with 16 plus 4 root 3 divided by 13. Okay. Lastly here, now we have a sum of two roots, but again, we're going to use the exact same trick. We're going to multiply by the conjugate so that only the squares of the first and last terms are going to be left over. So I'm going to multiply this by minus root 5, and same thing in the denominator, root 3 minus root 5. And so here we're left with root 2 times root 3, so root 6, minus root 2 times root 5, which is root 10. And in the denominator, we have root 3 times root 3, which is 3, minus root 5 times root 5, which is 5. Again, the middle terms cancel out because I have negative root 15 plus root 15, so they always cancel out. So I'm just left with here, this is negative 2, so I'll put the negative in front, root 6 minus root 10 over 2. Okay, and there you have it. So these are all the different ways in which we can operate or simplify with radicals, okay? And it's all based on using this property that comes from our exponent laws. Okay, and that's it for our operations with radicals.